So I've heard a lot of people talking about deep learning, and specifically a lot of people claiming that they're worried that it's overhyped. Um, so I'm a deep learning researcher, and I find these comments pretty interesting um, because, from my point of view, I think I feel the opposite way. I think I feel like the overhype of deep learning is itself overhyped. There's no question there's a lot of hype in the field. Uh, Sometimes there are articles written about it that are poorly informed, but does that really mean it's overhyped? So let's talk about some of the things people say they're concerned about. Uh, Here's one. Deep learning, it's just the latest fad. Next year it'll be something else. Well, it's a fad that's been a long time coming. Here is the first hardware perceptron, the basis of neural networks and deep learning, from 1957. What you're actually seeing in deep learning today is the result of decades of research. And those decades of research are finally getting to the point where they're actually giving state-of-the-art results. So it's not so much that this thing has suddenly popped up and now people are talking about it, but it's after all of this work, people have finally got to the point where it's working really well. So you should expect to see it continue to improve rather than disappear. But deep learning and machine learning, they're just the same thing, right? Or deep learning is just another tool like support vector machines or random forests or logistic regression, right? Well, certainly not true that deep learning and machine learning are the same thing. In fact, deep learning is just our way of doing machine learning. Before deep learning came along, this is how machine learning was done. Let's say you wanted to look at these breast cancer slides, as happened in this Stanford computational pathologist study, and create a 5-year survival predictive model. So in the classic approach to machine learning, what you would have to do is come up with lots and lots of examples of possible features, like relationships of contiguous epithelial regions with underlying nuclear objects, and so on and so forth. So you would have dozens of domain experts working with dozens of computer programmers and mathematicians to come up with these ideas for features and then to program them. And then you would put them through a classic machine learning model, such as in this case, it was logistic regression. Now, this computational pathologist paper was really successful. They came up with a model that was more accurate than human pathologists, but it took years and years of work. So that's kind of the classic approach to machine learning. Deep learning, on the other hand, combines these three things. It combines the neural network, which is a mathematically provably infinitely flexible function, with stochastic gradient descent, which is a way of fitting the parameters of that function to make it solve your particular model for your particular data set, and to do it in a fast and scalable way by using GPUs. And it's only in the last few years that these three things have all come together to actually allow us to use these neural networks to get state-of-the-art results. And so rather than having to do all of this very slow, error-prone, expertise-intensive feature engineering, what we can do is we can feed a totally random set of weights into our, we'll start with a totally random set of weights and then train them with stochastic gradient descent. And we can then go back and see what these neural networks learn. And so this is an example from Zeiler and Fergus showing what a specific neural network learns after looking at over 1 million photos. And so there are many layers, and layer one, these are the filters in layer one. You can actually draw them and see what they look like. So these weren't programmed, but it's learnt to find kind of diagonal edges and gradients and areas of color. And then on the right-hand side, we see examples, 9 examples of parts of a photo that each filter has identified. So when we get to layer 2 of a deep neural network, we start to come up with filters that are much harder to draw. On the left-hand side is an attempt to draw 16 of them. On the right-hand side, I think is much more easy to understand, which is here are a bunch of examples, 9 examples of a few different filters from layer 2 in terms of parts of photo they recognize. And so in layer 2, we can combine the edges together, for example, to find something which is recognizing corners. Um, we've got another filter in layer 2 that's recognizing lots of lines, another filter in layer 2 that's recognizing kind of orangey areas that are matching sunsets. Um, So layer 3 then can combine those together to find, for example, anything that looks like text or anything that looks like the edge of a flower. By layer 5, we've got things which are finding uh, the eyeballs of lizards and birds. We've got something that's finding unicycle wheels. And so in a deep neural network, these can be over 1,000 layers deep. So the kind of level of sophistication you can get when you have to pre-program your features in compared to the level of sophistication that you can get when you can learn hundreds or even over 1,000 layers of features, which each of which is multiplicatively more complex than the previous one, it's very, very different in terms of what it can do. And it's also much, much easier to do the neural network approach because you don't need all that domain expertise. So a very valid concern until somewhat recently is, well, deep learning sure looks great for image recognition, but it doesn't seem to do anything much else. Um, so the first thing I'd say is image recognition is actually really interesting and really important. So this is actually an example of a study I did after noticing that back in 2012 and 13 that deep learning was the clear state of the art for image recognition. I thought, well, what could we do with that? So I said to myself, okay, well, let's try seeing if we can do medical diagnostics better. So a team of folks and I spent 2 months looking at lung cancer CT scans and trained a deep neural network which had a lower false negative rate and a lower false positive rate than a panel of 4 human expert radiologists at identifying malignant cancer tumors in these CT scans. Um, so I would start off by saying, like, okay, it is clear that the state of the art for image recognition is deep learning, and it's surprising, how important that can be for real practical projects. I'll also say it's surprising how many things can be kind of recast as a image recognition problem. So for example, really the key piece of AlphaGo and the algorithms that have come since then, which have beaten the world champions at playing Go, is really an image recognition convolutional neural network. And specifically, what AlphaGo did was they looked at lots of examples of Go boards, which have been played in, actual human tournaments. And they said, okay, this Go board is an example where white ended up winning. This Go board is an example where black ended up winning. And basically they ended up doing a image recognition neural network where the thing that they were trying to learn wasn't, is this photo a cat or a dog, but is this picture of a Go board where white wins or a picture where black wins? And so they ended up with something where they could actually predict the winner of a Go game based on looking at the Go board. And so that was the key piece, really, to the success of AlphaGo and the things that have come since then. So there's a good example of kind of turning something that doesn't look like an image recognition problem, in this case, winning Go, into an image recognition problem. So in the Infosec community, one of my students did something very similar, which was at Splunk, they wanted to build an algorithm to help detect fraud. And as part of that, to detect whether 2 users were the same person or not, whether that person was associated previously with fraud. And so he wanted to use what he had learned in our course with image recognition to do that. And so what he did was he created these pictures you see on the screen, and each picture represents the mouse movements that the Splunk system has captured as somebody looks at a web page. And so you can see the actual path of the mouse. You can also see the color represents the velocity of the mouse, and then the circles represent left clicks and right clicks. And so in this case, he created a convolutional neural network, an image recognition program, to try and predict fraud based on these pictures. Ended up with a fantastically successful result, which ended up being patented, written up by Splunk and becoming part of their products. So here's an example of a very direct application in InfoSec of using image recognition. Um, but is it only useful for image recognition? Well, until recently, it was true that there were few, if any, state-of-the-art results outside of image recognition but that is no longer true. So in the last couple of years, that's been changing. So what I'd say works now with deep learning is lots of different kinds of computer vision tasks work very well, state-of-the-art results. You won't find anything better, and you can generally use off-the-shelf libraries to get them without too much effort. What you may not realize is also in the it works now, and when I say works, I mean better than any other approach, is for most NLP problems, for many, so that's natural language processing, so text problems, for many structured data problems, so where you've got like rows and columns of data like from a spreadsheet or a database, many time series and signals problems, when I say signals, I mean it could be a signal like a kind of order of events of different IP addresses connecting to your system. It could be some kind of IoT sensor, whatever. In all of these examples, most recently, I find most state-of-the-art results coming out are based on deep neural networks. So I would say this was also in the works now category, but that's in the latest research. So generally speaking, you're going to have to do a whole bunch of your own coding and training of neural nets and so forth to get really good results in these areas. But it's totally possible. And within the next 12 months, I think you'll see a lot of off-the-shelf libraries that work really well for these as well. I think equally important then is the what's not ready section. And so in terms of things where I'm seeing very few practically useful results right now would be reinforcement learning, adversarial models, and anomaly detection. There are pockets of limited success on certain restricted research problems, but I would say that these three areas are not areas that are kind of widely getting state-of-the-art results across lots of kind of different problems, particularly practical problems. This is a bit of a problem because lots of people are working on reinforcement learning, so lots of people are publishing in the area, and adversarial models and anomaly detection are obviously very important in Infosec. So the other thing I've heard is just deep learning's been tried a few times recently and it's just not working that well. So I would say that's somewhat true, but I think partly it's because a lot of people in InfoSec seem to be focused on this not ready part of the spectrum. And so in particular, if you look at AISec 2017, here is the deep learning session. And in fact, every single example is basically adversarial modeling. And so I thought that was really interesting that the deep learning session at this important ACM conference is all focused on stuff which the basic underlying techniques don't really work yet in the underlying literature. However, the good news is at NIPS, which is a machine learning focused conference rather than an InfoSec focused conference, there was a InfoSec workshop. And in that one, when I looked at their session one, machine learning in practice, really every single one of the talks was covering stuff which is definitely in the it works well right now section. So it's interesting to see that the kind of the machine learning community, I guess they kind of understand what stuff works and what doesn't, and they're more focused on the let's use stuff that works. Whereas I'm concerned that I've seen lots of examples of people in the InfoSec community using deep learning, particularly for anomaly detection and adversarial modeling, where I'd say we just don't have the tools at this point. So does that mean that we can't really use deep learning in InfoSec because adversarial modeling and anomaly detection are so important? I'd say no, it doesn't mean that at all. Like here's lots of examples of like basic classification problems that you could start applying pretty much off the shelf deep learning to right now. You could be doing DOS and intrusion analysis, looking at people's sign-up details or their IP and session history. So sign-up details would be like structured data. IP and session history would be like a time series or a signal analysis. They both work really well, state-of-the-art results with deep learning for finding spam or phishing. You could look at the message text classification, and I've actually got a paper coming out very soon, which will be showing clear state-of-the-art results with deep learning across every single classification problem we looked at with text. Um, Fraud, we've already talked about, finding similar users, using structured data, and so forth. And so I used to run a big email company, which I founded. And these were the kinds of things that we were doing all the time at my email company. And nowadays, if I was still running that company, I would definitely be using deep learning for all these things. So then I hear that, well, I'm interested in deep learning, but I can't use it because it's a black box, it needs too much data, it needs PhDs, it's only for vision, it needs lots of GPUs, it's not really AI. And these are all kind of, to me, just tired claims that just aren't true, or aren't true in very interesting ways. So like, the way that you understand a deep learning model is you can look inside the black box using all of these interpretable ML techniques. There's been various interpretable ML workshops recently and papers. And in the end, we're basically looking at visualizing the gradients and activations. This claim you need lots of data, it's generally not true because most people in practice use transfer learning, which means you start with a pre-trained network, which maybe somebody else has shared online, and then you fine-tune the weights for your particular task. Generally speaking, if you've got about 1,000 examples of a signal, you should be able to get a good neural network. In fact, my students have got very good neural networks with as few as 10 examples. Uh, it's no longer true that you need a machine learning PhD. Our library, fast.ai, and the Keras library now at Google are examples of kind of off-the-shelf libraries that curate and make available to you most of the best practices that you need. There are online courses and so forth. And there's lots of examples now, like thousands and thousands of examples, for example, of students that have gone through our course online with no particular background in the field and are now very successfully applying neural nets to their real world problems. You might worry that you need a huge room full of GPUs. That's really not true on the whole. The vast majority of successful results I see now are done with a single GPU. You generally see lots of GPUs for kind of big googly research projects rather than industry or commercial real world projects. And then we can have this whole discussion about, is it really AI, or is it going to lead to artificial general intelligence or whatever? I don't care about any of that myself. I know some people do, but it seems irrelevant to the question of, is this a useful tool that you could be using right now to improve your work in Infosec? So then the last issue I hear a lot is, well, deep learning sounds interesting, but I just don't know how to get started. I would say in the field of InfoSec, the key approach I would say would be turn your problem into a type that we already understand how to solve. So for example, if you think you have an anomaly detection problem, don't treat it as an anomaly detection problem, treat it as a classification problem. In other words, try and find a couple of different classes. So maybe just you've got one class called these were anomalies, or these were interesting security events would be more likely. And so now you can turn it into a classification problem where you're separating things into interesting security events or not. I would say adversarial models, why don't you just try skipping the adversarial piece to start with and build a model without worrying about that and see if it's effective enough. I find most of the time it is. And then I would say work closely with people in the deep learning community. There's lots of folks, for example, on Twitter, lots of open discussion, very high level of collaboration and openness in the deep learning community. And so you should find lots of people that can help you. And then finally, I mentioned we have a free course online, no ads, no cost. We're a nonprofit, so we make this available just because we want to help you out. And so if you go to course.fast.ai, we've got many dozens of hours of lessons to basically teach you how to get state-of-the-art results in a very code-first way, which we hope you might find helpful. Sorry that I couldn't be there to do this talk in person today, but really appreciate you listening. Thanks.